No? All right. What we have today is we have an unknown sample. This is our beaker here. And in this unknown, your unknown is going to be a white solid. There's going to be sulfate, and it's an unknown amount of sulfate. It's solid, meaning that these sulfate ions are trapped in some kind of crystal lattice here, and they aren't free to move. And so what we're going to do in the first step of this is we're going to add HCl. Actually, we aren't. We're just going to add water and see if it dissolves. If something dissolves in water, it tells you about some of the properties. It tells you that it's water soluble. But there are certain things that are not water soluble. So, for example, we don't know what the cation is. But there's certain cations that form insoluble sulfates. And so this goes back to your solubility rules that you learned in Chem 4 or Intro Chem. How many of you had to memorize the solubility rules for Intro? 2, 3. Just about 4 of you? 5? Yeah, you guys are going to be at an advantage because memorizing it, if you forgot it, it's much quicker the second time around. But if it's the first time that you're memorizing the solubility rules, you want to give yourself extra time. The solubility rules are going to be covered in Chapter 5. And so to give yourself the maximum amount of time, I would start reviewing those now. The ones in Chapter 5 are a little bit more complicated. The ones in our lab manual are a little easier to memorize. So I'd memorize the ones in our lab manual, which are identical to the ones in Chem 4. And start memorizing those. Does anybody remember the solubility rules for sulfate? Sulfates are all soluble, or all soluble except for which ones? Lead, yeah. What else? Mercury. Lead, mercury. Silver. Silver is borderline, but silver. What else? Calcium, strontium, and barium. And so if we have one of those ions, it's not going to dissolve in the water, at least the sulfate part. And so normally when an unknown is very difficult to dissolve, we try hot water. Hot water sometimes will get it to dissolve because things tend to be more soluble in hot water than in cold water. But if hot water doesn't work, what would you try? Cold water doesn't work, hot water doesn't work. You want to get your unknown to dissolve. What might you try? Acid. Acid. You can try mineral acids. Mineral acids are like HCl, HBr, acetic acid. If a mineral acid doesn't work, then you could try something called an oxidizing acid. An oxidizing acid would be like nitric acid, perchloric acid. Oxidizing acids tend to be pretty strong oxidizers. And that's why they're called oxidizing acids. And they're easy to differentiate because you just need to look at the oxidation states and you can figure out, is it going to be an oxidizing acid or just a mineral acid, a regular acid? If that doesn't work, then people usually try hot oxidizing acid, get it to dissolve. If it still doesn't dissolve, then you could try bases like sodium hydroxide. But, it might not be an ionic salt as your unknown, an ionic compound. Those types of things typically work for ionics. It might be some molecular compound, and could be something fairly nonpolar. And so all those are aqueous solutions, but what we might try to do is use something of intermediate polarity, like alcohols. Alcohols are a little bit like hydrocarbons, a little bit like water. And so If you suspect maybe it's not so polar, you can try alcohol. If alcohol doesn't work, you can try something like hexane. You know, hexane, what's that? Hexane. 6-carbon alkane. And pretty nonpolar. You can see if it dissolves in hexane. Hexane dissolves wax. And so actually yours are water soluble, and so it dissolves in water. Which brings us to the next step. You're adding HCl. And so what is the purpose of the HCl? And so this, you know, pre-lab quizzes, let me tell you, if I were to give a pre-lab quiz, I might ask something like, what is the purpose of HCl? You know, did you understand that from the reading? And so does somebody know the purpose of HCl? It's not to dissolve, it's to do something else. Precipitate. And so this is why we have this kind of pre-lab prep, because you have to go through the labs to understand this before coming in. This is something you definitely have to read. So at the bare minimum, you have to read the lab, right? But it would be much better not just to read the lab, but to do your notebook prep. Actually, how many people did their notebook prep? Okay. Yeah, you want to be careful because it's not enough. How many people did their notebook prep is not enough. But you might think, oh, my neighbor didn't do it, most people didn't do it, so I'm okay. No, that's not the way to think. You know, your neighbor didn't do it, most people didn't do it, then most people might be failing the course. It's not okay. You know, it's not average. And so you want to make sure. The purpose of the HCl is to prevent interferences. So we put it in there. But essentially what's going to happen is the water is going to dissolve your unknown. It's going to free up the ions. So we're going to have some cations. I don't know what they are. Maybe one cation or multiple cations. But the important thing is we've freed up the sulfate. So now it's sulfate AQ. When the sulfate was locked in the solid state, it couldn't move. You know, well, movement, there's different kinds of movement. There's, you know, translational motion. Translational motion is moving from point x1 to point x2. So there's no translational motion here. But in the liquid phase, you know, in the aqueous phase here, there's translational motion. So this sulfate's free to move now. And so we've unlocked it out of the lattice. There's also vibrational and rotational motion. So there's still motion here, you know, vibrational rotation, but the sulfates are kind of locked in position. And so the first thing is to free up the sulfate from the unknown solid, and that's what we do just by dissolving it in water. And now the sulfates are separated from the cations and whatever else is in there. There could be other anions as well. We don't know, plus other stuff. Okay, now what we want to do is we want to capture the sulfate. And so what cations like sulfate? Can you think of a cation that likes sulfate enough to precipitate out with sulfate? Barium, yeah. Calcium, strontium, barium, lead, silver, mercury. We don't want to use lead, silver, or mercury. Calcium, strontium, barium, it turns out probably barium's the best. Because barium, you know, we're going to use it as barium chloride here, which is an aqueous solution. Barium chloride contains barium ions and chloride ions. So we're going to use the barium ions to precipitate out the sulfate, i.e. we're going to use it to capture the sulfate ions over here. The problem is when we form the precipitate, the crystals are very small. They don't all fall down to the bottom of the beaker. Instead, what we get is we get a cloudy precipitation. cloudy suspension develops. And the cloudy suspension are barium sulfate crystals, but these crystals are very small, so they stay suspended. In fact, if the crystals are so small, they might end up being permanently suspended. That is, they'll never sink. There's enough kinetic energy to keep these tiny crystals suspended. And when that happens, we get a colloidal precipitate. A colloidal precipitate won't settle. We want this to settle, but it won't. But we aren't stuck, because with colloidal precipitates, we can get those to coagulate. To coagulate is just, to get the crystals to come and form these conglomerates of little crystals that weigh enough that they fall down to the bottom of the beaker due to gravitational forces. And so how are we going to get this to coagulate? Because what happens is we need to make sure we've captured all the sulfate. And so the way we're going to do that is we're going to add barium chloride here, and then watch it. If more precipitate forms, then we haven't captured all the sulfate. But the problem is this gets so foggy that you can't see if any more precipitate forms. It's impossible, because it's a milky white suspension, and you add a drop, and you can't tell, did you form more precipitate or not? And so in order to see, we have to get these crystals to settle to the bottom of the beaker, but we might be waiting for a very long time. And so how can we speed up the coagulation process, or how can we get this colloidal precipitate to coagulate? Yeah, we're going to heat it. We're going to heat it, and that's going to force these little crystals to collide and coagulate so that they fall down eventually to the bottom of the beaker. And so we heat it. We heat it, and the crystals grow in size. This. So heat. Actually, we'll get it to boiling here. And then we'll cool it on a ceramic plate. Okay, when we let it cool down, the crystal should fall down to the bottom and give us a CCS on top. CCS stands for clear colorless solution. Sulfate is colorless, and our unknown's white, so everything should be colorless. Barium chloride's colorless. And then now that it's nicely coagulated, we can add a drop here. When we add a drop, we'll watch it. The barium chloride is more dense than this solution, and so the barium chloride drop will sink in here. Eventually it'll diffuse, but diffusion is a little slow, so it just kind of sinks. And you watch it carefully. As it sinks deeper and deeper, do you get more cloud formation? If you get more cloud formation, then you haven't precipitated out all the sulfate. But, they say to stir it. If I stirred this, you know what's going to happen? If you stir this, what's going to happen to all this sediment down at the bottom of the beaker? You stir it up. It'll all mix up and give you a cloudy white suspension. Do we want to do that? No. If you're heating it and it's boiling, as it's boiling, it's going to kick up the precipitate and make it cloudy. And so if you really want to test this, you bring it to a boil to get it to coagulate, and then you cool it down, and then you test it. Why do you think they're asking you to stir it? Well, one of the reasons, I think, is maybe to get rid of any kind of concentration gradients. Concentration gradients are where, there's more sulfate in one part of the solution than there is in another. And to avoid that from happening, what you do is you test different regions of this. And so you put a drop here and watch it go down. You put a drop here and watch it go down. You put a drop here and watch it go down. So you hit it in different parts of the beaker and watch it go down, and then see, did any of those drops lead to additional cloud formation or additional precipitation? if yes, if you got precipitation, then you have to repeat. And you keep repeating until you get no more precipitate. Once you get no more precipitate forming, then we know we've captured all the sulfate that was in our original unknown and precipitated it out as barium sulfate. And so now all we have to do is we have to isolate that precipitate. The way we isolate that precipitate is by filtration. But the type of filter we're going to use is this. It's called a Celis crucible. And a Celis crucible has a fritted disc on the bottom. It's like this glass ceramic disc. Pores are very small. So I just filled this crucible with water, but do you see how slow that drop is forming on the bottom? It's going to take forever. And if your crystals are too small, they're going to clog all the pores in this, and you aren't going to get any drops forming, which means you're going to be filtering not just one lab period, but you'll probably have to filter over 2 or 3 lab periods in order to finish it. And so hopefully we don't get clogged crucibles like this. It's not paper here, this is ceramic, or glass. And so to make filtering more efficient, you want bigger crystals. To make bigger crystals, how can you make bigger crystals? Well, it goes back to here. On the addition of barium chloride, do you want to add it all at once? If you add it all at once, you make bigger crystals, or do you want to add it drop by drop, or slowly? What do you think will make bigger crystals? Slow addition of barium chloride or rapid addition of barium chloride? Slow addition, that's correct. Why? Typically, there are 2 processes occurring in crystal formation and growth. Crystal formation called nucleation. When you add a whole bunch, you might nucleate a whole bunch of tiny crystals. Those tiny crystals can't grow very big because there's not enough feedstock. And so what you want is you want to minimize nucleation. That is, you just want a couple, 3, 4 crystals to nucleate. And then those crystals you want to allow to grow bigger and bigger. Right? And so you try to minimize nucleation. Well, nucleation is done by different ways. Some people scratch the inside of the beaker to create, defects which crystals can nucleate on. Other people add seed crystals for nucleation. We can't add a seed crystal. Other people add dust or particles. Like when they go seed the clouds, they're seeding it with nucleation sites for water. That's one way, but yeah, sometimes it's hard to control. Another way is to do this coagulation process. This coagulation process has a different name, when we're heating it on the hot plate. When we're heating it on the hot plate, we're trying to digest the smaller crystals, make them bigger. And so what we want to do is we want to max the digestion. In other words, we want to just gently boil this for as long as possible. Because the longer we boil this, the bigger the crystal conglomerates will grow, and the easier our filtration will be. All right, that pretty much will wrap it up for today's lab. You're going to get the unknown sample from the stockroom over here. She's going to give you a tray. This is what it looks like. Oops. 34. That's mine. Once you're digested these, you let these cool down, and then you are going to store them in the cabinet over here, covered. Well, let's go back to this. here, what are the interferences that we're worried about in this particular experiment? The interferences are this. Does the only thing barium precipitate with sulfate? Is that the only thing that will precipitate with barium? What else might precipitate with barium? For example, hydroxide. If hydroxide was present in here, would that precipitate with barium? No. Because hydroxides are all insoluble except for calcium, strontium, barium. Group 1, ammonium. What other ions might be in here that will precipitate out with barium? Well, the other ions that might precipitate out with barium are carbonate. So we might form a precipitated barium carbonate or phosphate. You know, if our unknown contains carbonate, then we're going to get a white precipitated barium carbonate or a precipitated barium phosphate. Now, if we have a mixture of barium sulfate, barium carbonate, and barium phosphate, how can we separate out the barium sulfate from the other two precipitates? There's a very famous story about Pasteur. You know, he had two different crystals in a mixture. And what he did was, I think he took a microscope and tweezers, and just with the tweezers, he could tell by the different shapes, he got all crystals of one shape separated from all the crystals of another shape by hand. You want to do that? Well, one, you'd need an extremely powerful microscope because these crystals are tiny. And if they're tiny, you're going to have what, millions, billions of them? How much time do you have? Well, not enough. So is there another way? Yes, there is another way. We have HCl. So let's take a look at some double replacement reactions. Do you guys remember double replacement reactions? All right, barium sulfate solid plus HCl yields what? BaCl2 plus H2SO4s. HCl is aqueous, BaCl2 is aqueous, that's what we're using. H2SO4 is aqueous. Okay, then what do we do? What's next when you do double replacement reactions? Okay, that's, yeah, usually go to ionic equation, net ionic equation, but before we do that, we have to do something. It's balanced, I balanced it already. We have to do something else.
See if it will react. See if it will react.
See if it will react. How do we see if it reacts? Yes, strong acid, what? Can't form strong acid. Okay, what do we look for to determine if it reacts? Solubility, to see if we get a precipitate. What else? The activity series is for single replacement reactions, not double replacement. Activity series for redox. We don't use activity series. What else? We look for precipitate, we look for gases, we look for stronger acid to weaker acid. Anyway, this wouldn't be so great because HCl would kill our precipitate and revert it back to barium chloride and sulfate. And you know, we wouldn't want HCl because if we're trying to capture this precipitate and HCl is going to consume our precipitate or eat it up or destroy our precipitate, then it doesn't make sense. And so what we see is there's no precipitate, there's no gas, there's no stronger acid to weaker acid, so there's no reaction, which is a good thing. There shouldn't be any reaction here. Otherwise, it's not going to work. Whereas barium carbonate solid, if we form barium carbonate, what happens when we react barium carbonate with HCl? What forms? Here. What forms? No. No, that's not. We have plenty of HCl. Lots of HCl.
Oh, CO2 and H2O.
Yeah, CO2, H2ON. Double replacement reaction, so tell me what forms. Barium, chloride, and this. What is this? Carbonic acid. Everybody should know about carbonic acid. They know it's stable or unstable. It's unstable. And it goes to balance this. Is there a driving force for this? Driving force is there something to make this reaction go? Yes? Yes and no. What's the driving force for this? Did you guys do double replacement reactions in Chem 4? You did? Just 2 of you did? 3? Okay, I was expecting you guys to be much further along in this. We'll have to talk a little bit more about this. This is in chapter 5, we're going to talk about these. This driving force, gas formation, stronger acid to weaker acid here. Sorry, 2 driving forces for this. And then barium phosphate. What happens when barium phosphate reacts with HCl? We form barium chloride and phosphoric acid. Is there a driving force for this? Yes, there's a driving force. We're going from stronger acid, HCl, to weaker acid. Here. Then we got to balance this. So we need 6 of these, 3 of these, 3 of these. Balance. Then we need the states.
By driving force, do you mean what is the purpose of the equation of the reaction?
Okay, no. How did I figure out no reaction here? Do all reactions occur if I wrote it? Ah, heck, I have this reaction. Water goes to hydrogen gas plus oxygen gas. I just wrote that reaction there. I need one hand. Is that reaction going to occur? Sure, because I wrote it, right? I wrote it. And so if I have a beaker of water, I expect hydrogen to be bubbling off this and oxygen to be bubbling off of it. Right? No. There's no driving force for it. What's driving that reaction to occur? Nothing. Nothing's driving this reaction to occur. It's not going to happen. Not unless I have something to drive it. I can make it occur. This is what they say by separating compounds by chemical means. That chemical means is the way I'm going to drive that reaction to occur. Right? You guys, driving force, does it ring a bell at all? Not at all. Wow. Either you forgot it. Can't believe they wouldn't talk about it in Chem 4. Or
because I remember it being a situation where if your main goal is to precipitate out barium chloride, then the reaction will occur. It's a you form the weak acid or the strong acid, but your goal is to precipitate. Does that have anything to do with driving force?
if my main goal is to precipitate out barium chloride, we have in that hood number 3, we have a dropper bottle that contains barium chloride, AQ. My main goal is to precipitate that out. How am I going to precipitate it out? Right now it's aqueous. I want it to be solid. How am I going to precipitate it out? I got to do something. So what can I do? I got to evaporate all the water. This barium chloride is soluble in water, so if I get rid of all the water, then nothing to dissolve it anymore. So I just boil off all the water, and then I can get it to precipitate out. Oh, well, I'm doing something. I'm driving the barium chloride out of solution into the solid phase, but I'm doing something to force it to happen. Some things happen spontaneously. You know, have you ever heard of spontaneous? Spontaneous just means it just naturally occurs. When you combust methane, what all driving force is what's a more stable mixture? Methane and oxygen or CO2 and water? Did we do the methane combustion yesterday? Methane and oxygen or CO2 and water? What's a more stable mixture? CO2 and water. We call it more stable, excuse me. Stable because in nature tends to go from unstable to stable spontaneously. You know, if I put this up here, it's becoming less and less stable, right? And so I know, the beaker, if I put the beaker on the floor, it'll become more stable. If I put it and hang it off one of these tiles, it becomes less stable because we know, it wants to go from less stable to more stable. So if I let go of this beaker, it's automatically going to drop. This is more stable down lower. And so this is called a driving force. And so just because you wrote the reaction doesn't mean it's going to happen. Just because I wrote this reaction, I can't wish it to happen. If I could make this happen, then wow, I could generate hydrogen for free. And hydrogen's worth a lot of money. And so this is why people learn precipitation. Well, I can understand. Maybe you didn't do double replacement because if only 4 people or 5 people memorize the solubility rules, how can you do double replacement without knowing the solubility rules? But in this class, you're going to have to master it. And so that means you just have a lot more work because a lot of people have already done a ton of these. By the time they get to this class, they're going to be already a couple of steps ahead of you. This is what happened to me in physical chemistry. The guy that was sitting next to me, his basic chem covered so much more than mine. He was already like, if we're running a race, he was already like 200 yards in front of me. How am I going to catch him, How am I going to get, well, it's going to be a heck of a lot of work to catch up, right? And so the same thing, like I'm saying, the people who have it already memorized are going to already be 200 yards ahead of you. That means you're going to have to work extra hard just to catch up. You know, and that's the situation that I had. You know, I had to work extra hard to catch up because, you know, I didn't know. I don't know. You know, I don't remember that Heisenberg uncertainty principle. I never heard of that. I don't remember that, but lots of people did, and they're already way ahead. And so anyway, this is just. I don't want to make it like the person is 1,000 yards ahead. So this is why I'm giving you a heads up. Start memorizing the solubility rules now. Otherwise, if you wait until the exam 2 when you're tested on it, you're already too far behind. You know, some people say I'm too far behind. I'll just kick in the towel, quit. You know, right now. But we're still at the beginning of the semester, so you have time to catch up. Okay, that's it. Well, we need a driving force. Here's the driving force. So this reaction occurs, that reaction. So what this means is barium phosphate's unstable in acid. The acid will eat it up. Barium carbonate's unstable in acid. Barium sulfate, is it unstable in acid? No, it's stable in acid, right? Strong acid, like HCl. Okay. Any questions about this? Yeah. No. All right, we have just a limited number of these guys. These guys are really expensive, and everybody needs 3 of them, so we don't have enough of these. And so we're going to have to break up into groups of 2, potentially 3. You know, I don't know if we have to go 3. I think we're just perfect at 2. There's 17 samples. Everybody has to work with a partner. You can't work individually on this one because we just don't have enough sample. I know a lot of people prefer to work alone. This morning, 3 people preferred to work alone, but we had to group them. Yeah. And see. All right. Also, remember we have a limited number of these here. And I guess that's it, unless I'm missing something. Yeah, that's it.